for me, it was about showing you the discoveries that I made about the emergent behavior of Langton's ant. So there are some hidden things about Langton's ant that nobody knows about. One of them is it's one-dimensional. It's not a two-dimensional lattice. It's a one-dimensional lattice because that's what the maths says it is. And you have to use Occam's razor, and you have to use the algebra and rely on that, because that is the only truth, rather than just opinions. So does everybody have has anybody actually looked at the tutorials I put on Buzzword Salad with 1.html, the first lesson? Or would you like me to go through it and you follow? It's okay for people to talk. I mean, it's okay. Let's just move on with that one then. Let me share my screen. What I'm going to do. Okay, so one of the things that I'm going to do is I'm just going to share my screen, and I'm going to go to my website, and I'm going to show you how you can use my engine to produce Langton's ant. The one thing that you can't really do easily is to do trillions of iterations using Python or C or C++. It's just very processor intensive. I wrote a program in assembly language which talks to the CPU, and it utilizes every bit of clock cycle that's available. So it can do a terrific amount of processing in a very short time. And it interfaces with Octave or MATLAB or Python, whatever, purely through the net. So if I just share my screen, and hopefully everyone can still hear and follow me. You'll have to excuse me because I don't really know what I'm doing with Zoom. How do we do this advanced portion of the screen? There we go. Let's try that. Okay, hopefully you can see my desktop. Not sure what that's doing there. That's that one. Okay, so I'm just going to fire up my website. You can actually, if you run Linux, you can download my LCE program and use it directly in the directory with your MATLAB or software. But there's an awful lot of interesting Gaussian distributed data within. Just bear with me a minute. It was quite surprising at how organized Langton's ant actually is. It may look quite chaotic, but on a bounded surface, the chaos actually has a super attractor. It's not just a 104 highway, which will go on an empty lattice, but when it's trapped and it cannot move about, there's some very interesting mathematical properties. Wait. I apologize for not having sort of a strict regime or program for you, because really what I wanted to do was to let this sort of become sort of emergent and generic. Itself, we end up learning about something that we're all interested in, rather than just it being excruciating for most people and interesting for one. 1.html. Okay, so the very first page is does everyone know how to use wget? So if you just make a directory on your computer, I mean, how many people are using Windows? Does anybody actually have a Linux shell? I know Ben does, but would you rather maybe I should just do the tutorial myself so you can see how I do it. You can look at the data that's coming out. It's probably the best way. Let's go back to that one, and then I want to bring up my. Okay, so the first thing I'm going to do is just resize this window. That's better. Oh dear, oh dear. Okay, so if we copy that instruction, what that's doing is it's just going to bring down the M file that I need to use. And if I run Octave, I should be able to run that file. think that's it. Okay, here we go. So at the moment it's running Octave script, which is obviously very slow. So 12,000 iterations takes a certain amount of time. But then you suddenly saw how quickly my program calculated just 12,000 steps. Now, these images are just for comparison. So 1 and 2 are for what Octave produced, and plots 3 and 4 are what my program plotted. And as you can see, they are identical. So if I get rid of these, and then what I'm going to do is show you what was already done, and you can see that. Interestingly, as you can see, this is going more and more and more iterations. And then eventually, when you do so many, you end up with this image on the far left, which is just a complete mess. And this is the idea for data encryption, because this is actually Gaussian distributed on an infinite lattice. And I think I can prove that. Let's move on to the second one. Now here is so game programmers could use this algorithm for producing sort of weird textures for planets and terrain. If we move on to this one, this is a little bit more involved, but what you do is you plot Langton's ant, and it's very difficult to explain in simple terms. But this is the S-shaped graph. And what this graph represents is that as Langton's ant here is iterating, and it is going over the virgin ground, it has the ground that's never been touched, then what you get is you get a count for the first step. That's an occupancy of just 1. And then when Langton's ant comes back and revisits that square for a second time, then the second visit has a count. And the reason that it goes in this S shape is that in order to have a count of 2, you must have had a count of 1. So you can see that actually that's just an integral. This single here is an integral of the area under here for the total number of iterations. So if you count up this bar, and then you add this one and this one and this one and this and this, all the way up to the bit where you had the highest number of steps, if you integrate under this curve, you will get the total number of steps that was done, which is capital N in the Octave script. If you carry on doing these iterations, what actually happens is you get this very strange thing where actually you get an S shape right down to here like that, where the center point, if you differentiate that curve, you end up with this nice Gaussian curve, which becomes more and more typical bell-shaped as the lattice goes to infinity. That is an algebraic proof, and I haven't published that, but it's something I wouldn't mind discussing with somebody at a later date. That was quite an interesting one. Then what I discovered was that there was actually a relationship between the number of iterations and the number of and the center point of the curve. So what you end up with, if you take a half e cubed in the lattice, so 256 raised to the power of 3, and you half that number, that will give you the sweet spot for the number of iterations that are required to produce this this almost bell shape. Now it's not quite bell shaped yet because it's a very small lattice, but as the lattice gets larger and larger and larger, the highway becomes less and less and less of an issue compared to the chaos that it creates. And of course, on a lattice that is made up purely of black and white squares like a checkerboard, there is no 104 highway, so that sort of strange bit there doesn't exist. It is symmetrical, but you have on top of this a superimposed amount of chaos right in the center. And it just so happens that on a 256 by 256 lattice with 256 levels of grayscale, the most likely height that you will find on any given square at random is 128. And I found that one quite interesting. And that seems to be the same for all different sizes lattices, which have to be square, of course. Here we are again, we've got another one, and as you can see that this differential is shifted to the right. And what we really need is to get this to come right over here and then come down and go to the 256. I'm not sure if anyone really wants to learn how to use my software, but if you go to my website, which is this one here, and if you were to copy this line, for example, into your web browser like that, and I go copy, if I actually paste that into my web browser, I'll open up another window. What it'll do is it'll actually run the software, and what we're getting back here is all the gobbledygook that should have been saved as a binary file for you to plot. Hence, that's why in the software for the M files, it says once you've done this, then go and fetch the two files for printing. And on this one, that what we saw was actually the bar graph binary file. That is all of the data for these graphs. So here we've got two graphs. We've got a whole pile of iterations. And because I set the frame rate here to 2, what we've done is it's done 2 sets of 40,000 in hexadecimal iterations. Don't ask me to convert that. There it is, it's 335 million iterations. So you've got 335 million iterations to produce this, and another 335 iterations, that's about 700 million iterations to produce this one. If you differentiate both of these, you get these two offset bell curves. But as I showed you earlier on, if you get this sweet spot of a half E cubed, you can get this bell curve to actually sit on top of the next one. So then what happens is you end up with these two curves on top of each other. I think I've shown that one. These are alternating. You need to double that iteration, because this oscillates from being a negative one to a positive one. So what happens is this then becomes on top of there like that. And if you now take the difference between that and the one that's above it, you end up with some very interesting statistics that come out. So here is another where I've offset it. So rather than produce two plots like this, I am producing two plots like this one. It just makes it easier to work with. It's the same. And if you now take the difference between these two, which is the difference between 335 million iterations, which is the super attractor, where the primary attractor is the 104 highway, of course, what you end up with is you end up with this curve. And this single curve here is showing you the difference in these curves. This is at 335 million iterations, and this one will be at 700 million iterations. And what happens is the more iterations you do, the more lower and flatter this becomes. So at low iteration counts, you have a big peak, and there's the probability that it's going to be at 128 in the middle is quite distinct compared to the probability of there being 0 or 255 visits. But as time goes on, the likelihood of you finding a vast difference in the number of visits becomes less and less and less. This curve actually starts to flatten right out. And you can see that here. There is your first set of 335 million iterations. This is your second one here. And then the third one is here. And now you can take the difference between these two and the difference between these two. So with treating it as a three-stage polynomial, you can take a second order differential. And this is what you get. And as you can see, the amplitudes of here and here are getting less and less and less. These are the S-plots. So these lines here are becoming very squashed out, mainly because the resolution is in your axes is lowering. And they are still in S shape if you were to expand it out. So now, if we just keep going and we do more and more of these, what we end up with is we end up with a plot, which I can't seem to find on here. Oh yes, if we do more and more of these, this now ends up becoming, at the very top, becomes this. So here are your multiple S curves, which look like diagonal lines, but they're not. They're actually S curves all stacked on top of each other. These here are the differential of each of these plots, and this is the differential of that. So this is your first moments, and these are your second moments. And this is just a 3D view of that. So this this sinusoid you can see here, it's not really a sinusoid, it's this one here, and these sinusoids right at the back, which are very low in amplitude, are all of these. And I think that is a fascinating side to Langton's ant that nobody seems to be aware of. It's really, I just want to spread this knowledge. What else do we have? I think that one covers that. So as you can see, the bar graphs, plotting the bar graph bin file is done using the minus t. There's a minus t which we use in here, if I can find it. I might have got rid of that, and it's probably compulsory that it just gets it done. But this is how you get the bar graph bin file. You can plot this yourself. This is the number of iterations, and this is the number of frames. X, Y just tells you where you want the graph to start. And if you're looking at the bar graphs, it makes no difference where Langton's ant starts, because it is an enclosed lattice. And this is your initial direction. Now I have written a C program which will take decimal values, which are much more palatable for people, and that will then take the decimal values that you put with comma separated values into this format to drive my program, which will run native on a Linux shell, and it should run under an OS X shell as well. Okay, so let's move on to the last one, which is number 3, and this is a separate part to Langton's ant, and this was something I discovered a bit later on. But when you plot Langton's ant and you get the occupancy, this is like a heat map. So where it's red is very high visits, it's like top of the mountain, and all this blue area here is at sea level. And this is the 104 highway just propagating its way, because this corner, this one, and this one are all joined together. What happens with the rotations of the ant is if you sum up the rotations, every time the ant rotates left or rotates right, it increases sort of monotonically in some way. If you look at the lattice. Yeah, it's a bit complicated. We'll leave that for a moment. But basically, it just keeps going up and up and up and up and up. And this is the 104 highway being done, where you have a repeating theta. So there's 104 increments and decrements to give you the 104 highway. If you plot this over billions and billions of iterations, and I mean 2 to the 32 at least, what you get is you start to see a graph like this, where it rises up and up and up and up and up until eventually the entire area is so occupied by other occupancies that the ant can no longer do 104 highway. It's impossible. So at best, it hits steady state, where half the number of squares are black and half the squares are white. And obviously, as it tries to make black squares by turning right or left, that behavior then forces it, a bit like Daisy World, that kind of negative feedback system, which gives you stability. And again, this value here, where it's stable, is 1/2 of the lattice squared. So a 256 by 256 lattice has an area of 65536. And so this line sits at 32768, which is right smack bang in the middle. And it always goes at a maximum of plus 512 or minus 512, which is 2e, where e is the length of one side of the lattice. And that is a law which holds for any sized square lattice. I would imagine that if you did lattices that were where the x and y coordinates were of a different length, then you just simply multiply the two and take the square root, and that will give you the center point. it'll be an integer, so it'll be rounded up or down. That's an area of interest that I don't have time to play around with. But if other people would like to discover that, that would be a great thing to add to this research. Now, here is a very interesting plot. What you do to make this is you treat this as an XY coordinate. So all these values here, not these, because they're all they're changing far too much. What we're looking for is the values that are about from here onwards. And I just choose an arbitrary value. But again, there is a relationship between where the corner starts on this curve to the size of the lattice and the number of turns. If you now treat this as an offset for an X direction, as in this is increasing in X and this one decreases in X, what you can do is you can make another lattice that interacts with this one, and you can treat that as your Y-axis. And so if you have 3 of these independent to each other, then you will get 3 of these graphs. Now, if all 3 lattices are the same size, then X, Y, and Z will all give you the same pattern because they're running the same Langton's ant. However, if you make the lattices of a different size, then this sort of, I suppose it's like a Markov chain, really. It's just it's a process of turns which are based on the previous turns, etc., etc., etc. They will all be different because Langton's ant is running on a different size board. So where the turns are happening off grid, they interact with a lattice that's of a different size. So what you end up then is you end up with 3 distinct different X and Y and Z coordinates. And if you plot those, this is what you get. You get this beautiful structure where at the very beginning, the X, Y, and Z coordinates are pretty much the same because Langton's ant is identical on all 3 lattices. Just because one is a very big lattice and the other one is small, doesn't matter. Langton's ant is still doing Langton's ant. It's only when it starts going over the boundaries and coming back in on itself that you start to get this rich chaos. And it's here that you see where the ant has really entered that sort of steady state chaotic motion. And interestingly enough, this becomes more and more circular and ball shaped the larger the lattice becomes, and the smaller the difference between the 3 lattices that there are. And again, this software and the M files, I'm very happy to share, and so you can have a play and see how it works. I think that covers the program there. Would somebody, maybe I'll just go through the M file very, very quickly so you get an idea of how you can interact with my software. I think so exit. Exit. Just bear with me. There we go. Let's see if I can double that in size. Okay, there she is. That's it. What on earth have I done there? Sorry, guys. I don't know what I've done there. Absolutely typical. So here we go. We have, this is the Langton's ant that's done in Octave. Now this could be done in any computing language, from Java, Python, C++ to C to any language you want. I just chose Octave because it's open source and free, and it's MATLAB compatible. And this is just where it plots those 2 graphs. This one here, this little tiny Z on line 22, that is the inverter. So what this does is it's a 180-degree rotor. It just simply means that if it's black, it'll make it white, and if it's white, it'll make it black. That is the thing that inverts the square. This one underneath it, the big Z, just simply keeps adding 1 to each square that the Langton's ant is at, and that is your occupancy. So if the ant has visited a square 15 times, then this element in this array will be 15. And the element in the array big Z is actually pointed to by the array K, which is the ant. Now to visualize this, imagine you took a long piece of wire that had 656,536 atoms in it, and it was 1 atom wide, a bit like a sort of a graphene string, if you can imagine it. Now you wrap this around a sort of a torus or donut shape. What you end up with is a surface that's got 256 loops with 256 atoms per loop. And as you can see, if you go in steps of 256, you go radially along the donut. And if you go in steps of 1 and plus and minus 1, you just go along the string one at a time. And it just so happens that if you now make the loops almost to infinity and the granularity to infinity, you can make a surface that doesn't really, it looks like a flat surface if you make it large enough. And that was what gave me the idea for putting Langton's ant on that surface. When you bring the areas down to very small, like 6 by 536 and areas of 32, topologically they don't really work. But interestingly, when you apply it as a sort of as a quantum lattice, things get very, very interesting, because magnetic fields and electric fields are actually connected, because EM fields are, electromagnetic fields. And anything that's charged that accelerates will produce magnetic fields, and anything that is in a state of velocity will produce electric fields. And hence you can start modeling the behavior of electricity down a toroidal transformer. And that's where I led some of my mathematics onto to some very interesting transmission line equations. So this occupancy with capital Z and the binary lattice with little z, it's interesting. There's a chap called Oscar Davidson who discovered this, and I didn't even think about it. But if you actually look at bit 0 in the count for the occupancy, i.e. if your count is treated as a binary number, if you look at the least significant bit, which tells you whether a number is even or odd, so 3 in binary is 1, 1, but 2 in binary is 1, 0. So if the binary number ends in 0, it's an even number. If it ends in 1, it's an odd number. You can actually get the binary lattice from the occupancy just by looking at the low order bit. So we don't really need to do the oscillator. All we have to do is just keep doing the counter, because the binary digit 0 will keep alternating between 0 and 1 every time it goes up through a count. So that was quite interesting. So what we're going to do now is we're going to recreate this mathematical function as calls to the engine online. And what we have here is wget, which is telling my web server, which has LCEE running. This ELSEE.sh is a bash script that takes all of this string here and it presents it to my program, which runs. My program then outputs a report to say, was the code okay? Did it understand everything? Was everything all right? And it sends it back to you by this -o instruction and saves it as report.html. So you can look to see how it worked for you. Once you've done this, my program on my server will then save 2 BMP files of the iterations. It'll also save several other files with data in it. And it's these 2 instructions here. This one tells you to go to my server and bring back the B file. That's the binary file. That's the black and white squares for Langton's ant itself. BTX stands for Blade, Tau, and Zen, which is the name of my 3 children, and I just thought that was quite nice. This is exactly the same again, but we're doing the O file, which is the occupancy. And you can, if you convert this occupancy data, which is 8-bit uints, if you AND that with 1, so you're getting rid of all of the high order bits, you can actually recreate this B file here. So that's something that someone can have a play with. And here we just open that file that you just fetched, and it reads it in as uint8, and then it closes the file, which is important to do. It does the same for the occupancy for P and Q, and then we just simply plot them. Now, the interesting thing is, if I was to set this frequency here to 65536 frames, and I was to set this to 2 to the power of 32 iterations, it would take Octave probably an entire day to do the analysis. But if you use it through my program here, it takes about 90 seconds. And that's pretty cool, really, because it means you can do a lot of research at high iteration counts without it costing you all day. So there's a program called laca.c, which you can download and compile with GCC. And what this does is it allows you to use the same format, but you can use -xy with an x, y 3-digit decimal number. And again, -g becomes decimal. So you just put -g 12,000 in there rather than having to work in hex all the time. I work in hex because I'm just mad and I prefer binary and hex. I think that's all I can do there for that. Are there any questions? There's probably going to be quite a few. Has anyone visited the gallery that I made? There's a 3D gallery that I created. I don't know how do we get that? Let me just turn that off a minute. Everyone's very, very quiet. Was that just like, oh, screen sharing has stopped as the share window has closed. Is everyone still here? Anyone fallen asleep or lost interest, or is anything you would like me to go over again? Is there anyone here that would be interested in downloading my engine and trying to get it to run on their local machine? It won't work on Windows. It is a Linux binary, unfortunately, and it's written in assembly language. So I'm sending you the source code and getting you to assemble that. I don't think would add any benefit at all. You're more than welcome, I think. Where we go? Right, oh, sorry, we can see your website still, not the shell. We can't see your Octave window. Sure, I'd have a go this week. Okay, that's good. So if you go to buzzword salad, let me share my window again. There we go. Please feel free to put your microphones on and speak to me. It's I don't bite. Where can I go this week? Oh, recording is on. Right. Where would you like to go now? Would you like to see another demonstration of how I can get data out? Let's do that. Look, if I do xz w underscore now hopefully you can see the editor. That's good. That's good. What I'm going to do is I'm going to run that. I have to get rid of that for a second. I need to put and in there because I want to keep the window open. There we go. If I fire up Octave, now if I do compare again, look, run that. I have to wait. There we go. So what I'm going to do now is I'm going to get rid of all of this. I'm just going to edit this file and get rid of it. I don't want any of that. Don't think I need any of that. Save that. Run that again. Are you able to run through those again and tell us a bit more about them? Yeah, okay. Well, yes. I mean, it's the Brownian motion that I'm most interested in. That's the theta. I think really the best thing to do is for people to just learn how to use this software to say, so they don't have to spend all day waiting for their computer to compute. Because you can, if you know how it works, you can actually start to incorporate the code to drive it in your own code. And anything that you find interesting, please post it in my group on LinkedIn. I joined LinkedIn because I thought it's full of professionals. that's most likely going to find a professional on LinkedIn that's going to be interested in this mathematics. Okay, so that's just run. Why didn't it plot anything? Let's just run that again. Bang. Okay, so here we are. We've got plots 3 and 4 doing Langton's and. I am now going to go in and I'm going to change this 3, and I'm going to change that to that. It's quite a big number. And then I'm going to run that again. There we go. Look at that. Now that is, as you can see, this is the surface plot, which is very random looking, very random looking. It would be really interesting if people could find 3rd and 4th order differentials of these plots and let me know what you find. There's, this is telling us something. Langton's ant is trying to tell us that there is order somewhere in the chaos, and it would be really interesting to hear someone else's take on what they see it. So, for example, if you were to take a set of lattice sizes and play around with them, and they just happen to recreate, 6,000 lines of DNA code, that is interesting in its own right. I would find that most fascinating. It doesn't mean anything. It just means that it's an interesting, because each of the lattice sizes and the initial conditions will produce different outputs. So it's totally Turing complete. I know you're trying to help, sweetheart, but you can go down there and be quiet. Good girl. Okay. What else can we do? I'm going to change that, I think, to, let me try this and see if that works, because it would be nice to see if I could see that decimal version working. Let me just get rid of that for a second. Just bear with me. I think. There it is. If I do that. Okay, that's just brought down a whole pile of files. I think it's deck compare. Here we go. Here we go. So if I do X edit deck compare. Here we go. Let's increase the size of that so that it's more readable. So here's the Langton's ant math. And here is the decimal version. So if you do a system call in any of your software that has internet access, oh, that's not running. No, that's running native. This is it. Sorry, this is if you want to run it on your local machine. Apologies, that's the wrong one. It's a bit much when the person who created all this doesn't know what he's doing. I do feel for you all. This is all so new. There's just no information on it at all. But interestingly, Ben, I know you're into AI. Did you know that if you take a digital camera and you feed the lattice with the binary bits that come off the image, you can actually run Langton's ants from the sides and see them propagate across. And because Langton's ant can simulate logic gates, which has been proven, someone's made a digital clock using using NAND gates and etc. It's possible that you could have a set of state outputs that come directly from an emergent visual system. And if you plug that into neural networks and machine learning, you could actually see the very, very beginnings of real AI, as in it's not been programmed. This is an emergent response using Langton's ant as a propagator for logic to initiate and teach a neural system that if it sees a circle, Langton's ant will behave differently around that circle as an image. All of the data that it could hit thresholds that allow you to go, oh, that's a 1, that's a 0. So a lot of decision making based on visual input. Well, that goes for audio and light as well. So that's probably an interesting area that AI would be interested in doing, because it's not pre-programmed. It's not being set up by humans. It is purely emergent. by nature. Well, I forgot what I was doing. XZ. I think it's that one. Yes, there we go. Hopefully you can see that. There we go. That's a bit better. Yes, here we go. So on this system call, I would recommend everyone use this one because it is the easiest one to use. What it's using is it's saying that the -d says it's a direction, and we're having 2. -xy is now set to 128 across by 64 up. These are numbers between 0 and 255. -g is the graph rate, which is set to 12,288, which is actually 3,000 in hex. And the number of frames is just 1. And if you use this system, it just makes it a little bit easier to understand how to access my program. And again, declc is a bash script. It's like a sort of DOS program that takes this entire line of data and presents it to my program, which then does the processing and saves its files on my hard drive. You then access those files by downloading them with these two, and they are uints. So you can uint8s. So as you can see, you can just open the files and then plot the data that's in them. What else? What else would anyone like to talk about? I mean, my 3D gallery that I've set up has got a lot of material in there, ranging from quantum mechanics to game of life. I've created an equation for game of life. I did ECA, Wolfram's ECA rule 30. In fact, I've done 8 of them. I produced those 2 equations to try and garner some sort of to show that Langton's ant isn't a buzzword salad really. It's actually quite a sophisticated equation that people don't seem to understand, and I want to help teach people how it works and why it works. So I did game of life and I did ECA rule 30 to go, here's some well established cellular automata. Let's get some discourse going. Would anyone like to talk about the game of Conway's game of life equation? Yes. Oh, brilliant. Okay, look at that. Okay, so if we go onto Google and we Google Conway's game of... Actually, what I'm going to do is I'm going to do ECA rule 30 first. Hopefully that will come up. M5, I think it's that one. Yes, here we go. So here is the equation. And the reason why I'm doing this one first is actually if you take this equation and you put 2 of them together is in a 2-stage iteration, what you do is you get Conway's game of life. So this shows mathematically that Conway's game of life is made up from 2 different ECA rules. And that in its own right is very, very interesting. And here we see what we have is A is the number of bits, and ECA requires 3 bits, hence there are 256 different types, because their 3 bits are used for rule 30. Now in here we have theta, which is just a variable, and we're going to sum up all the bits from the far right hand side, which is bit 0, up to the number of bits that's in the system. So because it's a 3-bit system, it goes from 0 to 2. I think that's what I put into my script. And of course, what we have now is we have 2 to the power of A multiplied by the element in the array. Now, if it's a cell which is lit up, it's a white cell, then we have the number 1 there. Don't worry about this n plus a minus a. All this is doing is the minus a just goes from the right-hand side backwards. And so we start off by going 3 bits to the right from our current position, or is it 2 bits to the right from our current position, take away the run from 0 to those 2. So all this does here is it just takes the 3 pixels that are above your current pixel, and it simply says, let's sum them up in powers of 2. Once you've done that, you now have a binary number between 0 and 7, which is what 111 in binary gives you, isn't it? That is then used to give you an offset in trigonometry. Now, this is rather clever, I think. What I've done is I've put the pixels on the surface of a circle, around the circumference of a circle. And then by taking away 3/4 radians, what I've done is I've rotated that circle around. So it's a bit like barrel shifting the bits from the low 4 bits to the high 4 bits. So it's just a way of bit shifting. And then, of course, taking the arc sign just simply means we are going to drop off the ends, because you can't have anything greater than 2 pi. It just falls off the end. So this is a very nice way of shifting left all the bits using trig. And that then brings us back to basically this theta has been bit shifted by this number, which is just a ratio of 2 pi over this lot. And once you've done that, all you do now is you now take the element that you're at, and you just set the new pixel. And all this does is it just undoes the bits by then bit shifting to the right, so that now you have a number that's between 0 and 1. And if you just iterate this entire system, you can produce the ECA Rule 30 triangle. Now, interestingly, Wolfram uses the center line as a random number generation. But if you remember back at Buzzword Salad, my 3 tutorial, what we have here is we already have a beautiful system for producing random numbers, where the random number along this chain is actually very, very bell-shaped distributed. It has a peak of plus or minus 2e. It never deviates from that, which is quite fascinating, really. Why Langton's ant would go from here and work its way across to here, and then back from here and all the way back to here again. So it actually goes around in one circle and comes out the end. It never ever goes over that. It'll always go either in a straight line, or it'll actually do a loop and come out the other end. But it never ever rotates more than plus or minus 512, which I find very strange. I was not expecting that, and it doesn't make sense either. So if anyone would like to research that, make up different lattice sizes, and then take a Monte Carlo of all the different magnitudes for this. But yes, this will go on forever and ever and ever. On a 7x7 lattice, I did 30 million iterations, and I didn't see a repeat in this chain here, not at all. So on a 256x256 lattice, I should imagine it's probably in the order of 20 factorial at least before you start to see this repeat again. And that means that the lattice doesn't change its size, the amount of data doesn't change, because you can lose the previous data because you've already made your new step based on the previous step. Nobody cares about all the previous steps, so you can dump them, which means to produce a random number along here, or pseudo-random rather, you need a very small lattice, just a very large number of iterations. With Wolfram's ECA, which has a triangle, the triangle base has to become bigger and bigger and longer in order to create the next pixel in the center. And so for very, very long iterations, if you wanted to encode a movie with 60 megabytes of data, for example, then you would need 60 million lines on ECA's triangle, which if you think about it, would make the base at least 60 million pixels wide. And so, you know, it's just not, it's not doable. Whereas on this system with 256 by 256, you could keep iterating this for 60 million iterations, and each iteration, the ant will give you a new theta, a new torque value up here, and you just simply use that to encode. Because if you were to do exactly the same thing again, but on a lattice that had a single pixel in the middle, by the time you did about 1 million iterations, that Markov chain that you're seeing here would no longer be the same. So you couldn't decode it. You would need to know the exact starting conditions in the lattice, how many iterations were done before you could begin to decode any data that was encoded using this this string here. I think I've just gone off kilter there. So that was that's ECA, and let's have a look at the actual file. There we go. I'll just go over this very quickly because it doesn't actually have a lot in it. And I do have one that's even shorter than this. It actually uses the modulo function. There's only 3 lines. So this is the size of the lattice. I still use the Langton lattice. Remember, that's a string that's wound around a toroidal transformer. This is index. And the index, all that means is that to do ECA rule 30, you have to have a seed pixel, which is at the top in the center. So if it's 256 wide, then we need 128 offset to put us in the center of the screen at the very, very, very top. Little z is the entire length. So in Langton's ANT, this would be 6 by 536 long, hence e squared. Yeah. So it just sets them all to 0. So the whole array is equal to 0. And then it sets the Z index to 1. So this is a blank canvas with a single pixel at the very, very top in the center. This is the number of bits. And here we are going to sum from -1 to +1, vertically and horizontally, adding up all of the cells, just as if it was a noughts and crosses board, where the center was your pixel that you're looking at. And interestingly, because this sum goes like a noughts and crosses board, it sums up the center. We don't want the center. The center is the new value based on everything that's on the peripheral of that. And that's why we remove it later on. I think it's done here. It's so long since I've used this, I can't remember. I think that's what, let me have a look. Do you know, for the life of me, I can't remember what I did. But somewhere in there, you have to remove that bit for the sum. This is the sum. It'll come back to me. Delta is the same as the ant. So delta really is where is the ant? And because it doesn't have 4 directions, it only has one eye vertically downwards. Again, this a sine and sine business, what that's doing is like a ring buffer that's being rotated around, and we're just chopping off the bits that we don't want, and then we just update the lattice with the new value, and then we carry on, and at the end we plot it. And this reshape takes a single array of 65536 elements and turns it into a matrix of 256 by 256 and plots it as a heat map. Now, if we do Conway's Game of Life, you will see where the similarities. Where do I go from? I think it's that one. There we go. Conway's Game of Life. Here we go. We need to make this thing bigger. And then, how do you make that image smaller? Sorry, guys. Here we go. So again, theta, we're going to sum up oh, I know what I've done wrong now. On the ECA previously, it's not the peripheral, it's just the 3 bits above. This is the one that's got the peripheral, because Conway's Game of Life does the noughts and crosses board. I do apologize about that. Somebody should have said something. Yeah, I'll go back to that in a minute and re-go over that one. So what we have here for Conway's Game of Life is we have this is the left-hand ECA equation for Rule 30, but with a slightly different offset. But you can see the structure is the same. And this side is another ECA, and because they're mutually exclusive, what you have is you have Zn, which is the element, which is either a 1 or a 0, and here Zn is a 1 or a 0. So if this is a 1, then 1 times all of this plus 1 take away 1 times all of that means that if it's a 1, you get this portion doing Conway's game of life. If the cell is 0, then you get nothing times all of this, which means that doesn't get done. But now 1 take away 0 gives you 1, and you get 1 times all of this. So this just means that all that gets done. It's mutually exclusive. And again, we're barrel shifting round around the circle. So if you put your binary digits as the roots of unity around the complex plane, I guess, what you can do is, if you increase your angle, what you're doing is you're bit shifting around in a circle. And as you know, if you were to bit shift things at 720 degrees, what actually happens is they come back to themselves. And that's just like taking an 8-bit binary number and rotating all the bits by 8 bits. There's no change. Okay. And the reason why we use cos and arc cos and sine is that this very nicely saves me having to do an extra 180 degrees in here. Now, just interestingly, nobody knows this, but actually you can put 5 in there. Sorry, you can put 4 in there. And the reason you can put 4 in there is that this, interestingly, has the Pythagorean 3, 4, and then 5 is in the scale. It's a 3, 4, 5 triangle. There she is, let's see. So you have the 3, 4, and the 5 as a ratio. And that is something that needs to be investigated. I don't have the time to do that. It would be so nice if someone would take that. So in the octave script that you have, change that 9/2 to a 4 and play with it that way. But don't publish it, because one of the things that we have these days is people do tend to enjoy stealing other people's work and calling it their own. And so if this turns up in any books and is claimed that it's their work, then they're going to be propagating this error, and I can show that is incorrect. So it's a bit like maps. You know, they always put a bogus road in there to prove at the end of the day that is their map and it hasn't been copied. So that's the Conway's game of life. And again, my LCEE program actually will do Conway's game of life. You can load goal files from the Game of Life website. And if anyone would be brave enough to run my code and beta test it, that would be really cool, because it's only ever been really run on my machine and no one else. Okay, I think we're kind of done with that. Would anyone like me to go to my gallery and walk around it to show you other things in there that might be of interest? Are there any questions? Would someone like to, I'm going to stop sharing and hopefully people can talk. Do people want to talk? Oh, okay, yeah, I can show the gallery. Right. How do I do that? Here we go. So I will share the screen. There we go. Okay, so I'll get rid of that. ALife. So if you go to buzzwordsalad.com/alife.html, there's a link here which should show me the gallery. Here she is. Look, this link will take you to my gallery. So if I click on it, because I'm an administrator, I can edit it. So I'm going to have to be very careful that I don't drag pictures off the wall and vandalize the place. I normally use an Oculus VR headset for editing. Hopefully she will load. Here she goes. All right, so here we go. Very, very quickly, this is what I call a quantum tree. And and later on, I'll explain why I think this is a fundamental theory for the propagation of matter waves in space. This is like a normal tree, but I believe that if you look at Langton's ant and you work out this sort of this Brownian motion, which I'll show you later, you can see that this little tree structure, if you had billions and billions of these, you could actually make a tree. So what looks like something that doesn't make any sense to you whatsoever, on the larger scale, suddenly starts to show its form. And I think that's what Langton's ant is doing on very large lattice squares. I think it's going to start showing some interesting behavior. This is just a hypercube, which shows you that we're living in four-dimensional space, which I think we are. Here is the Langton's ant wave equation, all put up into matrix form. Now I particularly like this because it's so beautiful, and I'll show you one that's in 3D later. It looks a little bit confusing because some of the variables are a bit strange, and I'll try and explain those now. Psi x of t is a bog standard quantum string equation. It just takes acceleration and position from Hooke's law and combines it into the wave equation. Psi delta. Psi is the little z matrix. That's array. That is the array that's got 65536 elements in it. And this little delta sign is the ant. And the ant is going to be somewhere in this array. And it'll do 256 steps to go along the loops, or along the magnetic field lines, as I like to think of it. And it does plus or minus 1 steps to follow the Coulomb force, or the electric field, or that's 1 step at a time, forward or backwards. These are just the complex operators, just ignore that. The A is a half E plus 1, and that represents the size of the lattice plus 1. And if you half it, half E plus 1, and you multiply that by a half E minus 1, something magical happens, and you end up with this this equation that's for an ellipse, not for a circle. So A squared plus B squared gives you C squared, and when you set C to 1, you just get unity. But if you do 256 cos squared plus sine squared, what happens there is that as you rotate through the 4 cardinal coordinates, you end up producing -1 plus 1, 256, and minus 256, and that gives you a nice equation for an ellipse. Again, this is in quaternion space, so we have a J, we have a K, and we've got an I. Just ignore them. They're really there to keep track of the rotations. For the magnitude, it's more important to understand what's going on here. E squared is the size of the lattice, so this will give you a value of 65536 in the K direction. This is the sum going from 1 to all of the squares in the lattice, so E squared 65536, so there's 665,536 sums of psi delta. That should actually be n in there, but you understand that the delta is actually indexed by n itself. So if I put all of the variables in, this would look incomprehensible, and even I would get confused. So basically, we're just summing up psi delta. This is sort of a generic thing. That just means we're going to go for every single square on the chessboard from 1 to 65536, and we're going to sum it up. And hence, if there are 32,000 squares that are black and 32,000 squares are white, i.e. it's an equal number, then the total sum will be 0, because you're summing up an equal number of negative numbers as there are positives. This is the rotator. Now, this is the one that's quite interesting, because it basically rotates the ant. And it gives you those 4 different directions. How it does it is using Euler's identity, and there's plenty of maths on the internet to show you that one. Again, this psi delta here is exactly the same as this psi delta, and it just means that whatever delta is pointing at that time, your current square that the ant is on, we are hence if you take this and you multiply it by this using indices, then you add the indices. And so of course what that really means is that this angle here that's pointed to by these two is actually incremented or decremented due to this, and depending on whether that's a -1 or a +1 will tell you whether the phase angle for this and this goes up or down by 1. And IB is exactly the same as JA. It's just that this one is E-1 and represents for me, represents the magnetic field. If you now take this entire Oh, and because T is set to unity, so Langton's ant doesn't work with real numbers, it works with integers. And it basically assumes that at the very, very beginning of the lattice, where all of these squares add up to 1, 65536, and that is 65536. If you take the trace where you have negative ones stored in there, because you're with a biased starting grid where all the squares are white, then what happens is the trace of this matrix becomes 0. And it is this 0 fact that is why we have in the software here, in this equation, I have set this element to 0 and this element to 0 to produce Langton's ant. If you put E squared in there and other values, you're getting an energy equation, which makes no sense. Again, it needs to be investigated. But for Langton's ant, those two elements must be 0. So really, this is an energy equation that I've created, but at the initial start of a full array, that is 65536, take away the trace becomes 0. So that is Langton's ant when that is 0 and that's 0. X, because T is equal to unity, we don't include it because we're actually iterating. We're not so it's a bit like taking cos of an angle, and then instead of changing the angle, what we're doing is we're taking cos of the angle that we've chosen and we're going to iterate it, where the new angle then becomes the input to the output from the previous calculation. And so you have this iteration going on. So that's why T is not actually shown up in any of here, because it's actually set to 1 and we iterate. X is just a generic variable to say that we are working along, say, the x-axis. So all of the E's in here are actually X. But later on in 3D, I will show that E subscript X and E subscript Y and E subscript Z. If you remember, I talked about doing 3D Brownian motion, which had that ball-shaped thing with 3 different lattices. What you do is you take this and you treat that X as a vector. So it'll actually have 3 elements in it, which means this matrix now becomes a 6 by 6 grid, because it's going to have this for the top left-hand element, and then to the trace we'll have the EY, and then it'll have the EZ. And again, I think somewhere over here, I've actually shown that equation running, and I can't remember where I put it. Just bear with me a minute. Actually, what I'm going to do is I'm just going to run on very quickly. We'll go in here because I don't think we're going to have enough time to cover all this material. This is the graph of where I showed you that it went up and up and up and up and then hit saturation and became plus or minus 2e. This was the Markov chain that I was talking about, and this is like a random number generator. If you take the spectrum of this, i.e., you take the divisions from here to up to here and you cast them across, what happens is you end up with this graph, which shows that the most likely value that this has on the vertical scale is actually 32768. And the most least value that it's going to have is, well, it's going to be about here, which is plus or minus 1024, 2 times E, 512. You can see that you have this lovely peak. And if you take this first order differential of this, you end up with this. And of course, this looks like speech if you were to take a recording of some audio. And again, it would be really nice if somebody could take all this data and actually make sounds from what Langton's ant is creating. I think it would be a very interesting area of research. But as you can see, so here, there's probably only like 1 or 2 or 3 or 4 points that are along this bottom line. Hence, this has quite a low peak. Right through the middle, there's quite a lot of them that have got values. None there, and there's none there, but there's quite a few here. So that if you sum those up, you end up with this very high peak here. And of course, at the top here, where there's absolutely nothing, you can see it's completely dead flat. There is nothing there. Now, if you look very, very carefully, right down here is a tiny little circle with a magnifier on it. That is what this looks like. And of course, this graph here is the same graph that Langton's ant had on my website. which you can see anywhere. Slash. There we go. That's this plot here, look. So I don't know if you can see that, move that over there. So this plot here is this plot here, which is the number of times that the ant has rotated while it is doing its job. And as you can see, because it's all black, it's all turning right all the time. So this just keeps shooting up and up and up and up and up until it hits saturation. In which case you can see that it can no longer turn left and right very much. It can't deviate from that current value of torque, because every time it makes a black square because it's turned right, that black square then says into the future, you are now going to turn left. And so it literally is tethered to this value. This portion down here, okay, is this. And this is what you're seeing on here, okay? And if you look closely at this part, this is the very beginnings of Langton's ant. This is the round two-dimensional ball that you see for Langton's ant. And this is the highway. This is the 104. So each of these little sections is 104 sections long. So that's 104, that's 104, that's 104. You can see that this attractor, the 104 highway, continues indefinitely. It'll just keep oscillating. So there's proof in itself that if the lattice is big enough, that Langton's ant will continue doing the highway forever and ever and ever. There's no question of that, because it is a mathematical iteration. And it is this data here, because it is Gaussian distributed. And I can show you how I can make that assumption. Because if you look further up, on a lattice that's very, very large, that has done a tremendous number of iterations, this bumpy curve here is actually this beautiful smooth curve, because we are seeing millions and millions of these with a much larger spread of data. And here is your second order differential. It is quite smooth along these lines. It's only showing a bit of chaos at the very, very tips. And those tips are where you take this first order differential of where this crosses over. And as you can see, the larger the lattice and the larger the number of iterations you do, this now becomes a perfect sinusoid. And this becomes a bell curve with its mirrored top and bottom. But again, this does need to be absolutely proved with mathematics. I don't have the time. I'm so busy with sleeping and riding my motorbike and doing maths. So anyway, let's. If you ever go to my gallery, each of the gallery images has a little number underneath it in binary. Please email me. I love talking to people about this. So it's a real pleasure for me to meet people that are interested in this area. This is just a binary number, and it just references all of these images in the system. But I just wanted to cover that before I went on to anywhere else. There's a chap called Dr. Mark Agate, and he has basically taken the reciprocal world. So if you take 1/2 to give you a half, then a half would literally be 1 in binary with an infinite number of zeros to the right of it. And so what he's done is he's taken these integers and produced the binary equivalent. So 0.625, I think, is a half plus a quarter. I could be wrong, but that would be binary 1/1 with a load of zeros towards the end of it. And if you keep adding powers of 1/2 to the n in different values and different variants, you can actually add them all up to produce a number between 0 and 1. And if you take that string of ones and noughts and you force Langton's ant to turn right and left because of those digits in that reciprocal that you've created, not because of the inverting of colors, you get these plots come out. And they are absolutely amazing. They are showing some serious structure to how Langton's ant lattice, which is used as the new map. So the standard map, as you know, is just an XY grid where you plot all your differentials on. but I don't think anyone's actually plotted on a solenoid. And the benefits of a solenoid is that if you take a one-dimensional vector and wrap it round a donut shape, you can produce a bounded surface that works like a 2D grid, but is actually one-dimensional. And there is so much mathematics that's done in one-dimensional that can now be plotted in this two-dimensional way. And interestingly, something I'm working on at the moment is that if you now have multiple layers, then every 65536 steps along that array, you are now going not on the X and the Y lattice for Langton's ant, but you're also now going vertically. And that is something I am currently interested in. I'm working on that because that throws right back to gauge theory, which is a form of quantum mechanics on a lattice, on a quantum lattice. And gauge theory is quite new. It's and there's some very exciting research being done by that. And again, if anyone's interested in that, please let me know. Come and join my LinkedIn group. It would be so good to have people in there, even if it's just asking what the weather's like. It would be so good to get, because it's gone a bit quiet in there, and mainly because there's no information anywhere on the internet about this. It is a totally new subject, and people can break new ground. If you want to, I'll help you. I will help you dig up whatever you can. But here again, all this software is available. Very briefly, I don't want to bore you all too much, but very briefly, what we do. I don't know if you can see this. This doesn't help me much. What we have is you basically take your remainder. It has to be odd. You take your remainder and you multiply it by 2, and this is just basically long division. If you look at those 3 lines, it's nothing more than 256 into 65536 with the looks like a square root, and you do your long division. If that doesn't go into that, you put you carry the 1 and you do it underneath and underneath. That's what produces the long binary string as a loop. And this is the bog standard Langton's ant equation. So that was that. We are going to be running out of time pretty quickly. Again, this is ECA that was printed by my software, and that actually output a BMP 4096 pixels by 2048. Now, what my software can also do is it can also do differential. So it'll do a second one of these by adding to the previous, and some very, very strange statistics starts to come out. If you want to research that, I can get you kick-started on that, no problem. Here is the ECA equation. And I have to mention that all these paintings were done by my wife, who only discovered that she could paint just a couple of years ago. And I think she's absolutely amazing. So you're going to find a bit of her artwork scattered around the gallery. Again, here's the ECA equation in octave form. If anybody needs help converting this to Python or C, please let me know. I'm more than happy to help. No, this is a bit esoteric area. We'll leave that for the moment. So where are we now? So just bear with me. Even I'm getting lost in here. Oh, that's right. Yeah. So here we are at the beginning again. That's right. And if you head over to here. Okay, so this was the very first program I did for Langton's ant. When I first discovered it, I was actually watching Doctor Who. I think I was 20 years old, and I suddenly saw this come up on the Christmas lectures for children on television, and it just caught my eye. I just knew instinctively that you can't have a system that oscillates like this, and then it suddenly springs into a 104 highway. It means something. It means that there is sub-programming going on. It means that in mathematics and iterations, particularly for cellular automata, it means literally you are programming cells on how long they should live, how they should behave when they interact with other cells, and it's like a computer. So that suddenly gave me a whole new view of what DNA is actually doing, particularly when it's running magnetic fields and electric fields, which is basically what all the atoms are doing, which are inside all the chemicals that make up the RNA, which then make up the DNA. So here we are with my first attempt at extracting the statistics, because I was interested in where the occupancy was. Why were certain areas having a high visit rate when others weren't? What does it look like? So I thought I would code up the binary lattice here and the occupancy lattice here. So this is Lego shoes. So the white area means that the ant has been there rather a lot, and the black area means it's not been there at all. And again, you can see this little set of bar graphs starting to slowly work their way up. So now it's inside, it's now already working. So these bar graphs are going to be incremented. But once the Langton's ant goes on the outside periphery, it's going to be these bar graphs that get the attention now. And eventually, when it gets to the 104 highway, there will be a particular set of bar graphs which just constantly get incremented. So then I decided that let's see what happens if we let that run loose on a huge number of iterations. And that's what this video does. You can see that this is the occupancy. So it's an 8-bit grayscale. This is the 104 highway, and because it's this paper basically has been wrapped around a bun, a torus donut shape. Then if you leave this corner here, you'll come in at this corner, and if you leave at this point, you'll end up coming in about here. So this is just one complete surface. And the reason why you can't do this on a sphere, but you can on a torus, is that if you stick a pin in a beach ball and you take a long piece of string, which represents the vector, the Langton's ant, if you spiral it all the way around, covering the entire surface, you get down to the other pole, down to the other end. You cannot get back to your original starting point because the distance is too great. But if you were to take those two poles, push them together to give you a horn torus shape, now every step that you take, no matter where you go from where to where on that surface, you are guaranteed a uniform step. And that's why it has to be done on a torus, not on a sphere. Now this I'm going to try and I think you're just going to have to be patient, and I haven't got all day for that. So, but that will basically give you an entire surface where the most likely color that you're going to get is going to be 128, ranging from 0 to 255. So it's half. And I find that a very interesting emergent behavior of Langton's ant. It's very strange. Why would it do that? Again, these 3D models, which are object files, these are exported using my software. So you just put -obj in there, and it will output all of the pixels that it's found in its graphics, which can be imported directly into your 3D CAD software like Blender. Here is the paper that I submitted. I can't remember where I submitted it, but it basically, you can download this and read it at your leisure. There's no mistakes in it. I have thoroughly checked it. But it tells you how Langton's ant was created from first principles, and it takes you all the way through this very simple, like a direction cosine matrix, but in it's elliptical terms, hence 256 radius and a radius of 1. And it then shows you how from there we, now this is interesting. If anyone wants to talk about that, please email me. Go into the gallery, find these images and then email me. I would love to discuss them with you, and do it in my group so we can get a discussion going. And again, if we move through all of these pages, you can see how, again, this is theta, and there it is, the sum of all the elements plus or minus a half e squared. So if it's 65536, you sum up all of the elements, and that on as the limit tends to infinity will tend to a half e squared, as in 32768. That's that one. What else do we have over here? Yes, here's the donut shapes. So you can see the Langton's ant is on a donut shape, and then this here has been now wrapped around that. I used Blender to produce that. And further down here, this is a video of Langton's ant actually running Isn't that absolutely amazing? I mean, for me, that looks like staring at the sun and looking at all the plasma that's coming off the surface. It's got swirls and circles and arcs in here. This data that comes from here should really be investigated by a team, because there's circular patterns in here, and Langton's ant at the end of the day is using Euler's identity, which in itself is circular, but there's something that needs to be discovered in here. And again, I just don't have the time to do all of this. This is a very interesting plot. I let Langton's ant run for a very long time, and then I thought, right, I'm going to plot the dot cloud. So I took the all the values for the X, Y, and Z on every single one of these, and I opened up this this entire lattice into a long straight line, and I then plotted 256 along by 256 across by 256 up, and this was the dot cloud that came from it. And it's just, when you rotate this, it's just like a lattice gas. So it's a very good model for lattice gas dynamics, you know, if you want to investigate pressure and Brownian motion. Here is my software. If you, like I said, if you want to download my software and actually run it with your package like Python or whatever, it'll actually do graphics as well for you. You can record with software on your desktop, but again, it only runs in Linux. But here you see Langton's ant running the 104 highway. This is that bell curve that tells you the most likely value that's per cell. This is like the spectra from here. So as you can see, sort of round about here is 128, and that has got the most occupancies. It is in a state of being designed, so that's why all these things are looking a bit strange. That's the occupancy count, which is 32-bit with a 16-bit frame rate as well. I think that is the code that generates. That's it. Yeah. So here is the Langton's ant wave equation, not in matrix form, but it's been expanded. This is the one that's quite familiar on the internet. And here we are. This is the psi delta part. This is the plus or minus oscillator. This will either be plus or minus 1. This is the binary lattice element, and here is your psi and psi theta conjugate. They are basically, when you multiply these two out, two of them cancel, and you end up with E cos theta plus I sine theta. That is what distills out of this entire equation. And because this is multiplying this, what actually happens is that becomes your plus or minus 1 inside the angles. So it's E to the cos theta plus delta theta, which comes from here. What else do we have here? That octave script is this equation, and it just allows you to make sense of what's going on in here. It gets very interesting. This I don't think has ever been seen before. One of the interesting things that that I wanted to do was I wanted to see if Langton's ant could be done in 3 states, not 2, not 4. And I didn't like the way that the normal trigonometry gave you 2 crossovers on the 0 with a -1 and a plus 1. It's still 4 state. It's 3 state. It has 4 different types, and that's not what I was after. I was after a definite -1, 0, and a +1, and that is it, just those 3 states. And what I found was it was interesting. It came from some information I read about neutrinos and the flavors that they go through, and the 3 types of oscillations that they have. So I thought I would copy the idea of those 3 different oscillations, and I found that by putting the Fibonacci function into the theta for the sum for Langton's ant, if you run the MATLAB code, the octave code, what you actually find is that it will output either a +1, a -1, or a 0. And you can do that just by putting in here plot, plot delta theta. And that then gave me the idea from that to actually model the quarks on the complex plane. And quarks, as you know, they make up neutrons and protons. And I wanted to describe a way of doing fractional magnetic field as well as fractional charge. And so what you do here is you say these two magnetic fields collapse and cancel each other out inside the neutron. And what you end up with in the proton, what you end up with is an electric field moment, which you get in a proton. And here, the electric field components cancel out and give you a magnetic field moment. So if you take this magnetic field magnitude and this electric field magnitude and add this to this, you have a description for a proton, i.e. you take this one and you rotate it 90 degrees and you add it to itself and divide by 2 to give you the final answer. That's a description for a proton. But for a neutron, which has no electric field, what you do is you take 2 of these and you add them together. And what happens is the mathematics gives you a different value for a neutron and a proton. Hence, this extra rotation that's needed for this one to create this one, to add them to give you a proton, means that if you now rotate this one back again, as in it is a free neutron decaying into a proton, what you get is you get a value of energy for a neutron that is more than it is for a proton. And you can then account for the tau neutrino and electron being spat out when it decays. And that mathematical proof is shown here in 2 forms. It shows you as capital pi and as a sigma sum. And you can actually take the magnitude of these, which is what the capital pi is. You take the magnitude of those values as a complex number, they plug straight into the standard model with no changes whatsoever. But if you treat them as a complex pair, you can actually have a magnetic and an electric field moment, which I think is quite interesting. This is the Feynman diagram to back this up, and you can see that what's actually happening mathematically is that when a neutron decays into when a neutron decays into a proton, what's actually happening is all the spins are changing, but there's conservation of spin because they're not doing anything other than just changing their orientation with each other, they're just shifting around. But what is changing is that something has gone from having an acceleration down to it losing it. It is just at a velocity now. So this is like a car with its foot to the floor, stationary, and its wheels spinning out of the garage. And when the neutron decays into a proton, what you actually get is you get the car is no longer accelerating. It's in neutral and free flowing. And so now it's just coasting. And that is a sort of an electric field, magnetic field Feynman diagram. But you still get the same thing. You get a DDU into a UUD. So any theoretical physicists that are around would find that most interesting. Now this was born from an idea that I had for representing Langton's ant as a photon being shone on the surface of a torus, and where the photon is absorbed, the Langton's ant square goes white to represent it's just absorbed a photon, which actually, as you know, is all about conservation of momentum, etc., etc. And I thought, well, wouldn't that be nice if you could then say that when the square goes from white to black, it's actually emitting a photon. So you could treat that as sort of a photon absorption and re-emission from a laser on the surface of a torus that is electrically active, hence a very fine copper wire. And that's when I decided that if you treat these 3 vectors as Langton's ant forces for the pointing vector, which is E cross B, gives you a force known as the what's it called, the photoelectric effect and radiation pressure effect. This is the loop that occurs as a set of forces along the X, Y, and Z axes when you propagate Langton's ant. And it looks like sort of like a fishing line that gets whipped onto the rod. That's the eyelet that the line goes through. And it's a very nice example of how a photon has helicity, or an electron has helicity, depending on whether it's traveling towards you or away from you. And again, this is an area of theoretical physics that needs to be investigated. When you iterate this model for Langton's ant, you get this lovely Brownian string. These long sections, which are very similar and repetitive, are where the 104 highway is doing its thing. And as you can see, gradually it starts to deviate because the ants are all over the place now, showing proper chaotic behavior. And there it is on a 3D graph, just much longer. So I think this section here, which is only about 20 pixels long, very tiny, is actually this entire length here. But when this length goes to about a mile long, you get all of this. Okay. There's a portal here which you can go into and see Brownian motion for lots of other models. Now, going back to the telegrapher's equation, I propose that in electronics we have a shunt resistor. I've replaced that with a memristor, which is the fourth missing electronic component. And I've been playing around with the maths on that one, and I've come up with a couple of equations. So if you're interested in transmission line theory, not just for electronics, but for mechanics, I've made a mathematical map between the two. And it's proven to be quite interesting because you can derive mechanical pendulum equations from the electronic ones. And here, if you remember at the very beginning, I was discussing the very large matrix in 3D. Well, this is Langton's ant in 3D. And this is what it looks like. You have the I, J, and K elements, and you have your I, J, and K. Now, again, there's a deliberate mistake in all of these because I just don't want people copying and pasting, etc., etc. There is a duplicate J in here on I. Yes, so that should be KI. That should be a J, because then the J becomes with the K. So this is all right-hand, Fleming's right-hand rule. I cross J equals K. Vice versa gives you negative K. And this, again, is the 3D ball that gets plotted when you plot this, when you iterate this big matrix here. And it's most interesting. I think that really does need to be investigated. There's going to be properties inside this, but I don't know about you, but it almost looks like a sort of an atom bomb going off. So you could treat that. There is actually a fourth dimension of data, and that is the shading. I haven't bothered in here because it just made the plot look terrible. But depending on the color of each of these pixels tells you the amount of energy that particular pixel has, because Langton's ant was iterating and we've summed it up as Lego shoes. I think really we've done almost all of these things. Let me go back to your to this thing here. Let's see what people would like to talk about.